Well, friends, season's greetings from Total Output Power Solutions. I am Manohar Tatwadi, and today we are going to discuss about the fans used in power plants. And we will discuss about the fan performance measurement also. But if the time permits or otherwise, the video will be divided into two parts. So let us start. We start with the types of the fans and their efficiencies. The types of the fans those are used in power plants are centrifugal fans and axial fans. The centrifugal fans you can see here in the picture, the air in and air out centrifugally, and the axial fans are the input is axial and outlet is also axial. Now typical fan efficiencies. They depend on the types of fan those are being used, and the peak efficiency range is given in the table. The aerofoil backward inclined centrifugal fans, modified radial fans, pressure blowers, forward curved fans, axial fans are also there. So the different types of fans are there, and the peak efficiency uh, has been said in this table. Now the will come to know about the some terms. Here the term system resistance. We are going to talk about this. The system resistance. The system resistance. This refers to the static pressure. Now this system resistance is the total sum of pressure losses in the system. It's a function of the configuration of ducts, pickups, elbows, and the pressure drops across equipment. Now, you can take an example of a back filter or a cyclone wherein there may be some pressure drop across the equipment. Now, the system resistance it varies with the square of the volume of air flowing through the system. This is an important property. For a given volume of air, the fan in the system with narrow ducts and multiple short radius elbows is going to have to work harder to overcome a greater system resistance than it would be in a system with larger ducts and a minimum number of long radius turns. Some more points about the static pressure. Thus, the system resistance increases substantially as the volume of air flowing through the system increases, the square of the flow. Conversely, the resistance decreases as the flow decreases. To determine what volume the fan will produce, it is therefore necessary to know the system resistance characteristics. Now we talk about the fan curves. We have seen about the system resistance. We talk about the fan curves or the fan laws. Those have been given by the manufacturer. Fan curves are given by the manufacturers. Wherein fan laws, whatever fan laws, we will talk about that. The fan characteristics or the fan curves. Now the fan curve is a performance curve for the particular fan under a specific set of conditions. The fan curve is a graphical representation of a number of interrelated parameters. Typically, a curve will be developed for a given set of conditions, usually including fan volume, system static pressure, fan speed, efficiency, and brake horsepower required to drive the fan under the stated conditions. In the many curves shown in figure, the curve's static pressure versus flow is especially important. These are the fan curves and the system curves. The dotted curves are the system curves, and the dark lines are the fan curves. The fan curves have been at means they are drawn at a particular speed, maybe sometimes n2, sometimes n1, so at different speeds. And the Q1 and Q2 are the air flows. So you can see here in this how the pressure is dependent on the actually the airflow. It varies with the airflow or the speed or the system resistance. So these are the fan curves and the system curves together. The fan laws. Now the fan laws. What are the fan laws? Fan laws, there are three things to show. The flow versus speed. Now varying the RPM by 10% decreases or increases the air delivery by 10%. Means the Q1 by Q2 is equal to N1 by N2. The speed directly, the delivery is directly related to the speed. If the speed is increased, the delivery will increase by say 10%. In the second graph, you will see its pressure versus speed square. So reducing the RPM by 10% decreases the static pressure by 19%, and an increase in the RPM by 10% increases the static pressure by 21%. So the relation is something like that. The static pressure at 1 means static pressure 1 divided by static pressure 2 will be equal to N1 by N2 whole squared. It's related to the square of the speed. Now the power versus speed. If you compare the power, if the speed is reduced, then the power will also be reduced, but by the cube of this. So reducing the RPM by 10% decreases the power requirement by 27%, and an increase in RPM by 10% increases the power requirement by 33%. So these are the fan laws. Now we see about the fan performance assessment. How to measure the fan performance and how to assess the performance. Now we will see the terms before that. The static pressure, as we have already seen. Static pressure is the potential energy put into the system by the fan. It is given up to friction in the ducts. The friction will take some static pressure, and at the duct inlet, as it is converted to the velocity pressure. At the duct inlet, it is converted to velocity pressure. At the inlet to the duct, the static pressure produces an area of low pressure. Now the velocity pressure, it is the pressure along the line of the flow that results from the air flowing through the duct. The velocity pressure is used to calculate the air velocity. When we calculate the air velocity, we use this velocity pressure. The total pressure is the sum of static and velocity pressure. Velocity pressure and static pressure can change as the air flows through different size ducts, accelerating and deaccelerating the velocity. The total pressure stays constant, changing only with friction losses. Now the illustration that will show you how the pressure it changes in the system. The fan performance. So we measure the static pressure, velocity pressure and total pressure. This can give you a clear idea about the pressures, static pressure and velocity pressure. There is an air flow through the pipe. The pipe is there and through which the airflow is going. We have the manometers placed like this. One is the directly to the wall of the connected to the wall of the pipe. So here you can measure the static pressure that will be perpendicular to the airflow. In the second case, the total pressure that will be there acting on the particular pitot maybe, and then you will see that the total pressure will be given by the manometer is connected to the atmospheric pressure. The one end of the manometer is connected to the atmospheric pressure. In the third case, the other end is connected to the wall of the pipe itself. So that will give you the velocity pressure. The velocity pressure will be equal to the total pressure minus the static pressure. Now the measurement points where we will measure this velocity pressure and static pressure. So it is measured first of all in the return duct, or you can say the fan suction duct or the suction duct. Then the fan discharge duct at second point as the fan discharge duct, and the third point may be at the supply duct. So all these three you can measure the velocity and measure the pressures, and you can calculate the velocities. Now for this purpose you can use a pitot tube for measurement of static pressure, VP, this velocity pressure and total pressure. The pitot tube is something as shown in the figure. The inlet, there is a duct wall there of the pipe, and through which the pitot tube is inserted. It is an L-shaped pitot tube like that, and it measures both there are two ends connected to the manometer, and it measures the velocity, pressure as well as the static pressure. So the total pressure is measured here. Now we can take a sample example wherein now some plants you will get directly the measurement of the total air that is flowing, that you can take it for assessment, but may be corrected after that, and the equipment must be standardized or the tested. A sample example we can take. Now there is an FD fan which handles cold air at 30 degrees centigrade. The duct dimensions are there. It's a rectangular duct, 1.4 meter, 0.8 meter width. So the duct area is calculated. Discharge pressure, when it was measured, it was 140 millimeters of water column. The suction pressure was minus 30 millimeters of water column. The motor is a 6.6 kV motor. The current is 22 amperes. The power factor is 0.58. So you have to calculate the overall efficiency of the fan. This is an example, we take it. So first of all, we calculate the air or the gas density that is flowing through the fan. The first calculation is to determine density of the air or gas. Now to calculate the velocity and volume from the velocity pressure measurements, it is necessary to know the density of air. So the density is dependent on altitude and temperature. T degrees centigrade is the temperature of gas air at the site condition, or it can be taken from the temperature density curve. Here in our case, we have calculated the air or gas density gamma at this equal to 273 into 1.293 divided by 273 plus the degrees centigrade, that is 30 degrees, and it comes out to be around 1.165 kg per meter cube. Then the velocity calculation. So once the air density and velocity pressure have been established, the velocity can be determined from the equation. Velocity meters per second will be equal to Cp into root of 2 into 9.81 into Tp into the gamma divided by gamma. So Cp, where Cp is the pitot tube constant, that pitot tube constant has been given as 0.85, or it may be given by the manufacturer. Tp is the average total differential pressure measured by the pitot tube, or by taking measurements at number of points over the entire cross section of the duct. Now, Y, that is the density of air or gas at the test condition. So this velocity in our case, it comes out to be around 41.273 meters per second. Now the air or gas volume in the duct can be calculated by the following equation. Volumetric flow, that will be equal to velocity multiplied by area. So here the duct size, we have got the area, duct area. The volumetric flow has been calculated, and it comes out to be around 46.22 meter cube per second. Then the power output of the fan, that will be equal to the volumetric flow into the total pressure divided by a conversion constant of 102. So it comes out to be 77.04 kW, and the power supplied to the fan motor is root 3 VI cos phi, and that comes out to be around 145.866. So the overall efficiency of the fan, the overall efficiency, which would be equal to the power output of the fan divided by the power supplied to the fan, it comes out to be around 52.81. So this is how we calculate the efficiency, overall efficiency. Now this is from a typical energy audit of a FD fan, wherein the actual audit of a FD fan was done. Here the rated power of the FD fan, design value, and it was compared with the actual value. Now it was for a number of units, and we are calculating it for the 1 unit. So that can also be seen here. So the overall, you will see here the overall efficiency in particular. The design value is around 53.25 and the actual value is only 21.27 because there is only one fan in service. But still, you can go like this, you can have a typical energy audit of the same. Then how there are means you can have the energy saving opportunities. So how you can save the energy for this? Minimizing the demand on the fan. So minimizing excess air level in the combustion system, you can reduce the FD fan and ID fan loads. Minimizing the air in leaks in a hot flue gas path to reduce ID fan load, especially in case of kilns, boiler plants, furnaces, etc. Cold air in leaks increase ID fan loading tremendously, and due to the density increase of the flue gases and induct choke up of the capacity of fan, resulting as a bottleneck for boiler or turbine itself, boiler furnace itself. In leaks and outleaks in air conditioning system also have a major impact on energy efficiency and fan power consumption and need to be minimized. The findings of performance assessment trials will automatically indicate the potential areas of improvement, which could be one or a more of the following. You can change the impeller by high efficiency impeller along with cone, change of fan assembly as a whole by higher efficiency fan, then impeller derating, maybe you require a small diameter impeller diameter, change of metallic glass reinforced plastic GRP impeller by the more energy efficient hollow FRP impeller with aerofoil design in case of axial flow fans where significant savings have been reported. You can do this also. Then fan speed reduction by pulley diameter modifications for derating, options of two-speed motors or variable speed drives for variable duty conditions. Now these have been done in many cases. Then options of energy efficient flat belts or cock draw edged V belts in place of conventional V belt system for reducing transmission losses. Adopting inlet guide vanes in place of discharge damper control, minimizing system resistance and pressure drops by improvement in the duct system. So that's all falls here. I once again thanks for watching. Please comment, like, share and subscribe to the channel Total Output Power Solutions. So I take your leave, Manohar Tattvavadi.